Earth's core is stuck in the past. Literally. Time there is lagging 2.5 years behind time at the surface. And that's not just some quirk of Earth's core. We're all in slightly different eras. Your time is different from my time, which is different from the microbe at the bottom of the ocean, and the yak on Mount Everest, and the astronauts on the International Space Station. Even my feet and my head are experiencing slightly different versions of time. That sounds like science fiction, but it's real. And we know about it because with clocks, we can measure not just time, but also how time interacts with gravity. The connection between time and gravity goes back to the 1900s, when Einstein predicted something known as time dilation. It describes how time passes at different rates for different observers, based on their relative velocity or the strength of the gravitational field they're in. It's one of the weirdest things about our reality. Einstein wasn't the first to discover time dilation, but he did go on to develop the most complete theories and the best explanations for it. The first theory, special relativity, tells us that the faster someone moves with respect to an observer, the slower their time appears to be moving from the point of view of the observer. So, if you're on Earth and watch someone fly by in a rocket ship, their time is dilated. Einstein built on that theory to develop his theory of general relativity, which says that the more strongly gravity acts on you, the slower time passes for you, compared to an observer in a weaker gravitational field. To understand that, it's helpful to think about the way Einstein pictured the universe. According to his theories, space and time are linked in something called naturally space-time. And the way we usually picture space-time is as sort of a fabric that's tightly stretched, like a trampoline. Objects with mass, like say Earth, sit in space-time like a bowling ball on a trampoline and bend the fabric. That bend in space-time is what we know of as gravity. And the more mass an object has, the more it bends space-time, or the stronger its gravitational pull is. And since time is part of that fabric, the mass of an object also distorts and stretches time. And the closer you are to the center of a big gravitational mass, like a black hole, the slower time moves. Here's another way to picture that. Say we make a really basic clock with light bouncing between two mirrors. One tick, or second, on the clock corresponds to the light beam bouncing off both mirrors. Then, say we place one of these light clocks on Earth's surface, and an identical one way out in space. The curve of spacetime means that the light in the clock at Earth's surface will follow a curved path between the two mirrors. Light travels at the same speed in both clocks, but it will take longer for the light to travel between the two mirrors at Earth's surface. In other words, the clock at Earth's surface will tick more slowly. If you're feeling skeptical, that's totally fair. But general relativity is one of the most tested theories in physics. And time and again, experiments and practical applications have shown that Einstein's predictions are pretty solid. Time dilation can be seen most clearly by using atomic clocks, which are super accurate because they measure time based on the ultra-fast oscillations of atoms. More specifically, one tick or second on an atomic clock is equivalent to more than 9 billion oscillations. And in stronger gravity, it takes longer for those 9 billion oscillations to occur. In experiments, atomic clocks installed on skyscrapers and satellites were found to tick faster than the ones at ground level. Most GPS satellites carry atomic clocks, and at those elevations and speeds, the clocks run 38 microseconds faster than clocks on Earth's surface. One team of physicists even measured the time dilation of two clocks situated only 1 millimeter apart. Of course, we're talking pretty tiny numbers here. With a 33 centimeter gap in elevation, the difference in time dilation only accounts for 90 billionths of a second over a period of 79 years. That means by the end of my life, the top of my head might be just 90 billionths of a second older than my shoulders. So you don't have to worry too much about whether your apartment is on the ground floor or the top. But in some other cases, these tiny differences can matter a lot. Take satellites. Small differences in gravity can have a huge effect. Without accounting for relativity, satellites can desync to the point that after a day, your GPS directions would be off by 6 miles, and it would just keep getting worse. Scientists are experimenting with atomic clocks on the International Space Station too, since a future moon base or long-haul spaceflight would need super accurate clocks for navigation and communication. And here on Earth, we're experimenting with measuring minuscule differences in gravity due to differences in height above sea level. The ground often shifts before volcanic eruptions and earthquakes, which would shift the position of an atomic clock and change how fast it runs. With a network of atomic clocks, we can monitor these small changes and make better predictions. Or we can measure melting ice and rising sea levels to help us monitor the effects of climate change. These kinds of very precise time and gravitational measurements are essential for all sorts of science and technology. And with the ability to map the universe's gravitational landscape down to the millimeter, we may be able to find out more about what makes up that landscape and answer all kinds of questions about everything from black holes and dark matter to quantum states and the nature of time itself.